Okay, so let's start. Do you have any questions? Today we will start with a small discussion on general relativity. And then we will continue with the particle properties of waves. Now, when we were discussing special theory of relativity, what was our initial assumptions, initial postulates?
Yeah, the inertial reference frame, no acceleration.
So we are in an inertial reference frame. What's an inertial reference frame?
Newton's second law holds.
Newton's first law. How do you test Newton's first law?
If there is no force on an object, it moves at constant speed or at a standstill.
Okay, if there is no force, you have to observe the speed of the object relative to you. And then if there is no force, if the velocity of the object is not changing, then it's an inertial reference frame. So can you give some examples of an inertial reference frames? The surface of Earth, is it an inertial reference frame? Not exactly, but approximately, yes. So you have one inertial reference frame, and then if you have another reference frame which is moving at constant speed, at constant velocity relative to Earth, then it is also approximately at least an inertial reference frame. So what if you are in an elevator that is falling freely? Is that an inertial reference frame? How do you know?
Because there is acceleration, gravitation.
Well, you see, if you want to talk about acceleration, you have to be talking about some other reference frame. But imagine you are in the elevator and it is falling freely. So how can you tell whether it's an inertial reference frame or not?
Or can we?
Or can we tell whether it's an inertial reference frame or not?
You can look at the floors are moving without any force that I don't know.
Well, you see, I look at the floor. The floors are at rest relative to me. They are not moving.
No, the floors around the elevator.
I look around. They are closed, so they are not moving relative to me. I cannot look outside.
If there is acceleration.
Is there an acceleration?
If there is acceleration,
Okay.
they feel the force.
Okay, how do you test the acceleration of the elevator?
The light there.
The lights, well, let's not use the light yet. But what kind of experiment? I mean, you see, you had defined the inertial reference frame, claiming that it is the reference frame in which Newton's first law holds. Okay, that's the valid definition. Now I'm asking you this question. There is this reference frame. You are inside the elevator. And for an outside observer, the elevator is just falling freely. Being inside the elevator and unable to look outside, can you tell whether you are in an inertial reference frame or not?
If you are in the Earth and the elevator is moving, at some point we have to levitate.
Well, okay. Let me ask these questions. You are saying that if we are moving, but without looking outside, how can you tell whether you are moving or not? You are in a closed elevator. Will you be levitating? Assuming the elevator is falling freely.
Yes, you should. If it is accelerating, you would feel a change in force that is exerted on us.
How? How do you measure it?
Didn't you say we cannot know whether it's accelerated or not?
Well, we didn't yet assume that we didn't yet discuss general relativity, so we don't discuss the light yet. But you are on the right track. We basically cannot tell whether it's I mean, we can tell that a freely falling elevator is also an inertial reference frame. So you see, it is accelerating for an observer outside. But nevertheless, you will not be levitating unless you hit the floor with some force.
It is like, we feel the levitation when elevator accelerates.
You feel a reduction in your weight. You just compare the two. Before the elevator starts and after the elevator starts, you compare the two. That's what you actually feel. You feel the difference. But if the elevator is falling freely, and in that case, you cannot tell whether you are accelerating or you cannot distinguish whether you are in free space, no force acting on it, or you are accelerating in a gravitational field. In fact, that is how they create these zero-G planes. You basically go on a trajectory that is the trajectory of a freely falling object.
Can ISS be an example for it?
ISS, not really. It's not really a freely falling object. The thing is, ISS, there are rockets constantly pushing the ISS up. So because of that, it's not a freely falling satellite. The astronauts are not really weightless there. But there are other satellites which are freely falling. Well, this is an example where acceleration relative to some other observer cancels gravity, again, relative to some other observer. So that was kind of a hint that these two things are probably equivalent to each other. And of course, there was also the case we had studied. Let's say you are not in a freely falling elevator, but you are in an elevator that is in empty space. Well, you are in an elevator and you feel the weight. You are in an elevator. Well, just like, okay, if there is Earth here, you are falling freely with g. Your acceleration should also be g. In that case, no experiment that you can do will tell you whether you are accelerating or whether you are in empty space.
If you're moving inside the air, we should feel the air friction. I mean,
sure. Well, you see, that's why I draw the elevator. The distance of the elevator from the Earth is huge. There's one other catch. If you have very precise equipment, if you are in a gravitational field, then the acceleration of the bottom, will be different than the acceleration of the top. That's also another way you can actually tell. But assuming you are in a very, very small reference, if you are locally at least, let's say, if your elevator is sufficiently small, there is no way you can distinguish gravity from acceleration. And hence, you can actually use acceleration to cancel gravity.
This elevator and we are aware of the outside, which experiment will prove we are accelerating?
Well, you will be accelerating relative to Earth, or Earth will be accelerating relative to you. Just like motion is relative, acceleration will also be relative. Just measure the distance of Earth relative to you, and you will be determining its velocity and hence its acceleration. Well, if you are not looking outside, no way.
If you left your two objects, you would see that they are closer to each other.
You see, that means you will be looking outside.
No, inside the elevator.
Well, okay, so what do you mean? You have two objects.
You let go,
Okay.
and they're going towards the center of the Earth.
Okay. You too.
So they're getting closer to each other.
Well, yes, but of course, if the elevator is big, if the elevator is infinitesimally small, then they will not be moving towards each other. each other also. You won't be able to determine that also. Which basically states that locally, this is important, locally, for example, as your friend has pointed out, if you have two different masses, since they will be going towards us, the same point, they will approach each other as you are falling. And then you can tell that you are actually in the gravitational field of a circular spherical object. Or if you compare the accelerations at this, test your Newton's law here, Newton's first law at this point, and at the top, you will see that at least in one of them, Newton's first law will not be satisfied. Again, that requires you to make measurements at separated points. The larger that distance, the larger the effect will be. But those things are not local measurements. You just you compare two measurements done at different points. Locally, you cannot tell it. Yes?
Peki bu asansörde mesela elimizde bir çakmak tutarsak, çakmağında yakmayı yakarsak ateşin farklı şekilde bölündüğünü anlayacağız. Yani gerçekin yüzünden yukarı değil de bir yuvarlak olduğunu anlayacağız. Bu yüzden hocam ivmelendiğimizi söyleyebilir miyiz?
Well, you see, if you do that thing in a freely falling elevator, it will be circular. It will do, if you do that experiment in space, it will be circular. So you cannot distinguish whether you are in a freely falling elevator or far away from any mass in the space.
Peki hocam o yani Fransa'daki zero G uçaklarının önce makro G yiyorlar. Orada da hani bayağı hissediyorlar ivmelendiklerini.
No, they don't feel the acceleration.
Ama hocam yere yatıyorlar özellikle hani şey olmaları için.
When they stop, when they get out of the trajectory of a freely falling object,
Önce yukarı tırmanırken yere uzanıyorlar hani tam düşmeye 45 derece açıda düşmeye başladıklarında artık o deneyleri yapıyorlar. Yani o yüzden ben de şey düşündüm. O yüzden ivmelendiklerini hissetmiyorlar mı? Makro G yerken.
well, you see, just like one of your friends had pointed out, like in the elevator, you do feel that the elevator is accelerating by comparing how you felt before and after. But before and after are not freely falling states. One of them is not a freely falling state. So you feel the difference. Just like in these planes also, you do feel the difference. But while you are freely falling. I mean, if you want to tell whether you are in a plane, the only thing you need to do is just look out the window. You can also tell that you are accelerating towards Earth. Earth is nearby. But for a local observer that cannot look outside, he cannot distinguish. And we believe that the laws of physics should be local. So if locally you cannot distinguish, then those two things should be the same. And I repeat, this is because of the fact that the inertial mass is equal to the gravitational mass. Otherwise, this equality does not hold. Well, this says that actually they are the same thing. Local, again, I repeat, locally, they should be the same thing. So if you want to see what is the effect of gravity on any object, what you can do is you just go to a reference frame which is accelerating where there is no gravity. We know how to calculate the effects of acceleration. So that tells us how to calculate the effects of gravity. Well, you see, that equality tells me that if you are standing over here doing some experiments, or if you are some mass over here looking at the mass, testing Newton's first law, if this equality didn't hold, then you will be accelerating differently than the mass over there for an observer on Earth. That would tell you that if you are aligned at some point, in the future, you will no longer be aligned. Which will tell me that this observer can tell whether he is under the influence of gravity or whether it is accelerating. Because if you look in the elevator, you don't feel any weight, let's say. There is no weight. So you test Newton's first law. What do? You take that mass. You take a mass, stop it over here, isolate it from any other force. It should stay there, right? Now, if you look at the outside observer on Earth, and assuming that is not correct, it would mean that under the influence of gravity, you and that object will accelerate differently. So even if you are aligned at some given point, you won't be aligned at the next point, at the next instant. So inside the elevator, what you will see is that you will see this mass to go up or down relative to you. Because according to the outside observer at least, your accelerations are different.
Her yerde böyle mi? Bütün gezegenlerde, bütün uzayda, her noktada böyle bir şey mi? Yoksa sadece
You mean that equality?
empty space'te mi tutuyor? Unique olarak?
Well, you see, how do you test that equality? Well, we tested on Earth. We didn't test it on anywhere else. What did we do? We took two different masses in vacuum. We take two different masses, and we just drop them. If that equality holds, they should have the same acceleration. Otherwise, if they don't have the same acceleration, although they are different masses, this equality will not hold. You see, if you think of the laws of nature, where did we test them? Only on Earth, plus several tens of kilometers above Earth. Maybe you can count the moon. We have tested our laws, our understanding, only up to the moon. But when we look at further beyond the moon, we look at the sun, the planets, the other galaxies, the other stars, what we see is consistent with the laws that we know. So that kind of tells us that the laws that we discovered on Earth or near Earth should also be valid all around. Not just on Earth, but everywhere in the universe they seem to be valid.
Hocam burada Einstein Newton'un dışında yaptığı şey, hani Newton'da diyordu zaten gravity'de bir acceleration'dır diye. Ama
No, Newton didn't say that.
Ama hocam biz gravity ile ilgili bir şey yaptığımız zaman dünyanın onun çekimliğini acceleration kullanarak yapıyoruz.
Sure, but what Newton does, you see, Einstein says that these are the same thing. Newton said that, well, there's acceleration due to gravity, they are separate things. They can be equal, but that's mainly a coincidence for Newton. For Einstein, it's a necessity.
Newton'la ilgili işlem yaparken ben buradan bir taş fırlattığım zaman onu aya kadar aynı acceleration düşünerek yapabiliyorum. Yani
Okay.
acceleration düşünerek yapabiliyorum. Ama Einstein için ben buradan taşı attığımda ona bir acceleration verdiğim zaman o aslında gravity'nin ta kendisi mi olacak Einstein'a göre? Yani böyle bir eşitlik. Ben onu çözemedim.
Now, what kind of an equality? One thing that we had also discussed on Monday was whether light bends under gravity. You see, if you look at Newton, light doesn't have any mass, so it shouldn't bend under gravity. But Einstein says that gravity and acceleration are the same thing. So if you want to study the effect of gravity on light, well, you can look at the effect of an accelerating reference frame on light. And you can just imagine an elevator which is moving upward with an acceleration a. According to an observer on the elevator, if you just shine a light beam horizontally, initially it will be horizontal, then it will just bend. Well, it bends because the elevator is starting to move faster and faster in this accelerating reference frame. So according to Newton, okay, fine, no further conclusion. But what Einstein does is saying that acceleration and gravity are the same thing. This is exactly the same thing as you have an elevator under the influence of a gravitational acceleration whose magnitude is a. So here there is the mass. Einstein says that these two are the same thing. Since in this case, we have an elevator that is accelerating relative to an inertial reference frame, the observer will see the light bend. Here we have an observer at rest relative to an inertial reference frame, but there's the additional gravity. So that equality tells Einstein that light should bend. They should have the same thing, because this observer, without looking outside, he shouldn't be able to distinguish this case from this case.
Hocam acceleration'ın farklı yönde olması bir şey değiştiriyor mu? Yine light aynı şey.
You see, again I repeat, here what I'm talking about is the acceleration of the elevator, which is in the upward direction. Here, this is the gravitational acceleration, which is in the downward direction. And they have the same magnitude. Let me say this is A. So here there is a gravitational acceleration, and their magnitudes are the same.
Is the elevator falling in the second place?
No, it's at rest. At rest relative to the inertial observer. And the mass is also at rest relative to the inertial observer.
Why does the light in the second one bend towards upwards?
Why should it bend upwards?
Because it's going down and the first
It's not going down.
up.
No, it's not going down. It's at rest. You see, let's say we have an inertial observer, the eye, and it has an acceleration. Here, let's imagine another inertial observer, again the eye. Relative to the eye, this is at rest. And this is also at rest. They are not moving. The only difference is that this is under the influence of a gravity, which creates a gravitational acceleration for objects, for falling objects. So if you would just drop something, it just goes down. But this elevator is at rest for this observer. And Einstein says that these two things should be the same. So that is why here the observer should see the light as bending, but there's no acceleration to bend the light in this case. The only thing that can bend the light is the gravity. And hence Einstein concludes that gravity affects light also.
Hocam, normalde bir force uyguladığımızda objenin de force uyguladığımız yönde gitmesi gerekiyor.
Okay.
Ama buradaki mass'in gravitation'ı kendisine doğru çekiyor. Yani mass'in direkt olarak gravitational çekip çok
Okay, this mass will also accelerate upward. You see, this mass is exerting a force on light. Light is exerting a force on this mass. You see, Earth is pulling you. You are also pulling Earth.
Onu hareket ettiremediğimiz için light'ın hareket ettirmesi lazım.
No.
İşte
Both of them will be moving. But that's not really my case here. But this mass can be doing whatever it likes. The only important thing is that this mass is creating a gravitational acceleration. Meaning that at the point of the light, if I drop it, if I drop an object, this mass should cause that mass, that object, to accelerate with an acceleration equal to that one. If that is the case, then this observer and this observer should see the same thing. They cannot distinguish the two scenarios without looking out. You see, in this observer doesn't see this mass.
Peki o zaman şöyle bir soru sorayım. Şimdi gravitational force'u hissettiğimizde eğer konservatif olduğunu varsayarsak potansiyelleri farklı olacak yukarı ve aşağıdaki.
How do you measure the potential? Well, and I repeat, I am always assuming that my reference frame is small enough. It's a local phenomena. The elevator is very small. And if you talk me about the potential, I will tell you how do you measure it. How can you distinguish this case from that case? I mean, you can distinguish the potential difference because if there's a potential difference, there will be an acceleration. There will be a force enhanced acceleration, right? So you will probably say that this point has a larger potential than this point, so an object released from there should move towards here, right? That is what you will claim. But that will be exactly the same thing that happens over here. If you release an object from here, since that object, if there's no force acting on that object, as long as it's flying in the elevator. So the elevator is accelerating, that will be moving at constant velocity. So that object and the bottom of the elevator will come closer to each other in both cases. And hence you cannot distinguish the both cases. That was the postulate of Einstein. Some other questions from behind? There is no reference frame in which the light is at rest. Such a reference frame does not exist. There is nothing such as somebody moving at the speed of light. Okay, so? I mean, you see, here, I didn't specify the speed of this object. It doesn't matter. For some observer, it will be at rest at this instant, maybe. For some other object, for some other observer, it will be moving downward, and accelerating upward. For some other observer, it will be moving at this direction with almost the speed of light and accelerating upward. It doesn't make any difference. What do you mean hızlanmak? Are you introducing a second acceleration to the problem? Why not? It will see that the light will be bent. Why shouldn't it see the light bent?
But both of them bending at if two objects are in the speed of light, two of them
You see,
bending.
Okay, so let me clarify it a bit stronger. What are we comparing? We are looking at an observer at rest in the elevator. He looks at this light which is initially sent horizontally. If the elevator is moving upward if the elevator is accelerating upward, he will see that the light bends. That is the claim. Of course, you can just imagine many other masses around here moving with different velocities. It can be flying in the elevator, etc. But what I'm looking at is an observer at rest in the elevator and a light beam sent horizontally. I'm comparing this with the elevator at rest relative to some external inertial observer. There is a mass just below the elevator, and there is a light beam sent horizontally under the influence of the gravitational influences of this huge mass. Those two things are what I'm comparing. And what Einstein tells me that the observer inside the elevator cannot tell, should not be able to tell whether he is accelerating relative to some inertial reference frame or he is at rest relative to some inertial reference frame but under the influence of gravity. So that is what Einstein says. He cannot distinguish the two cases. But if he cannot distinguish the two cases, that also means that if light bends in one case, then light should also bend in the other case. But here, the only thing that can cause the light to bend is the mass. Of course, you can arrange your detector such that your detector will just move along the trajectory of the light beam. It can go down. It will see exactly the same thing. So it will just see as if the light beam is going horizontal relative to you. But so what? You see, that detector will not be accelerating in this reference frame. It will be at rest. And it will not be accelerating. In this reference frame, it will be accelerating downward. And then he will say that there is the gravitational influence of this huge mass, plus there is the gravitational influence of the other mass on the other side because he's accelerating downward in this reference frame. That is why there won't be any bending of the light, because these two things will cancel. That is what he will claim. He might claim, let's say.
John, what do we call this interaction? I mean, the gravity attracting, two masses attracting each other is like, we know that it's gravitational force, but I guess if I'm not wrong, 2 years ago or last year, when it took two black hole collision, the Nobel Prize thing, the Bayram Hoca gave a speech, and he said, I guess the mass of the photon, like something, if I'm not wrong. What do we call this interaction? I mean, how do we represent this interaction without saying that they must be equal?
Well, first of all, you start with saying that we know that two masses, they attract each other. And we call that gravitational attraction. What do you mean by you know that?
Yeah,
What we know is that if you put two masses nearby, the distance separating them will get smaller and smaller. That's what we know. And we identify that as they are accelerating, and hence their momentum is changing, so there is a force acting on it, because force we define as the rate of change of momentum. Well, the same thing here.
So do we have a mass of photon?
Well, the mass of photon is a different thing. So what Bayram Hoca says is that on one hand we have these colliding neutron stars. On the other hand, we have the gravitational waves. So we can look at the neutron stars, they will emit light, and we can look at when the gravitational waves arrive. If they are both moving at the same speed, they should arrive at the same time. So what we observed was light and gravitational waves, they arrived at the same time. But light is moving at the speed of light, at c. But that means gravitational waves are also moving at c. So if there is gravitons, well, we will come to that in several weeks. If there are gravitons, that means just like photons are massless, hence they are moving at c, the gravitons are also moving at c, so they should be massless. Now, there was a question from the back. Yes.
Hocam şimdi aslında söylediğim kısmen de doğru. Biz ivmelendiğimizde herhangi bir şeyde uzay zamanda bükme yaratmıyoruz değil mi? Ama çok büyük bir cisim varsa uzay zamanda bükme yaratıyor. O zaman bunların arasındaki farkı algılayabiliriz.
So let me write your sentence. If we are accelerating Are we bending the universe? So let me start with, what do you mean by accelerating? Relative to whom? So I always advise you to make sure that your words, your sentences really mean something physically. I mean, this sentence is grammatically perfectly correct. There is nothing wrong with that sentence grammatically. But some of the words over there are not well defined. So most of your confusions are due to the use of words which are not well defined. So try to realize them and try to fill in the gaps. You see, even when we were discussing about the garage and the car, well, you have a problem also in the assignment. The confusions between which reference frames to use were due to the fact that in daily life, we are used to being vague in the concepts that we are using. But in physics, we have to be more precise what we mean. Okay, there were some other questions. Well, define your question. Well, you are resisting in defining accelerating. The next question will be, what do you mean by bending?
Asansörün içinde birisi gözlemliyor. İğmelerin ortaya bir tarafından çekiyor. Bu gözlemciye göre ışık hızı sabit mi?
Nice question. Locally, again, in this very small elevator, the speed of light is again c, locally.
We said that the photon pulls Earth and Earth pulls photon basically.
Photon?
Pulls Earth and Earth pulls photon.
Okay.
They pull each other. So we knew that gravitation was due to mass, but photon doesn't have mass.
You say, what do you mean by we knew that gravitation is due to mass?
We observed that.
Newton said that. Newton had made observations which he interpreted as a force created by the mass. But then there is this Einstein. Einstein now says that there is no such force.
Can I ask something else? If light can bend under acceleration, then wouldn't we have different results in Michelson experiment?
Well, let's see. Now I will be asking, what is bending? If light bends under acceleration, how much difference do you expect? Well, let me give you some numbers. We did test the bending of light. So there was this, the Earth doesn't have too much mass. Sun is thousands of times, has more mass than Earth. So there was this, so Sun would probably bend light more than what Earth would do. So if there is, let's say, some star over here, and if the light passes very close to Sun, it should bend, and if you are on Earth looking at the star, you should see the star over here. Well, the star is actually towards the right, but you will see it towards the left. If gravity bends light. But of course, for practical reasons, this is not usually possible because you cannot see the stars when there is the sun. And furthermore, you require the light of the star to pass very close to the sun so that the effects of gravity will be larger. But luckily, in a solar eclipse, you can see these stars. You can determine their location when the sun is not there. And you can determine their location during a solar eclipse when the sun is there. And the difference, this angle, did you read the book? Do you remember how much? I think it was arc seconds. This is very, very small. So you see, Michelson-Morley experiment, when it proved that the speed of light is the same for every observer, you cannot prove that. What you can prove is that the change in the speed of light for different observers should be less than such and such. That is what you can prove, what you can measure. And that difference, the precision is, I think, 1 part in 10 to the power 16 or something like that. 1 part in 10 to the power 16. So if the speed of light is 10 to the power 8 meters per second, that is 10 to the power, the error bar is something like 10 to the power minus 8 meters per second, if I'm not wrong. But the error bar is really small. Some of that error bar will be caused by the gravitational effect. But you see, even that will be, their contribution will be even more negligible because it's a horizontal apparatus. If you would do it vertically, then it might contribute. But it's horizontal. So the effect will be really negligible, if any. Other questions?
Hocam, kozmolojik sabitin bu hata payında yeri var mı? Einstein'ın kozmolojik sabit.
I don't know. I don't expect it to have any influence. Now, this is not an error bar, by the way. This is the actual deviation.
Yok, ben significant figure'daki hatadan bahsetmiştim.
Okay, so now let's come to the other question. We talk about straight lines. What do you mean by a straight line? Okay, we will talk about straight lines. We didn't yet talk about them, but we will. What do you mean by a straight line? Come on, don't be afraid of pronouncing things that you already know. Shortest distance between 2 points. Okay, how do you define the shortest distance? What do you mean by distance? You see, the problem was, even in special relativity, we had seen that distance doesn't really have any meaning. Because distance changes from observer to observer. So it doesn't really make a good definition if you talk about just the spatial distance between two observers, the space-like distance between two things. It will change. In optics, you should have seen one principle, for example, Fermat's principle. Do you remember it? Least time. Well, why does the time change? Well, you have different medium. If you don't have different medium, then the speed of light will be the same everywhere. So basically, this would mean that the light will just pass through the smallest distance. So light goes along a straight line, as straight as it can get. But not, yes, question?
Buradaki bükülme de zaten onun straight line olduğunu gösteriyor.
That is a straight line. That is as straight as you can get between two points in a meaningful way. So that is actually what we mean by bending. What you are actually minimizing between 2 points is this one. You try to minimize this one. This is a meaningful quantity for every observer because it will be the same. Well, let's see what does it mean that objects bend? The space-time is bent. How does this explain, how does the bending of light is related with the bending of space-time? Now, let's look at an apple. Let's just imagine that this is the horizontal. At this point, you shine some light. And also from this point, you shine some light. And let's say that you shine them horizontal to the equator initially. Do you know the shortest distance between 2 points on a sphere, as your friend had defined before? It's the big circles. That gives the big circles, meaning that, let's say, if you have these 2 points.
We are on the surface.
Hmm?
We are on the surface of it.
Yeah, we are on the surface. This is the center. This is the shortest path. Now, let's say, not this direction, but from the equator, you shine 2 lights parallel to each other. Well, what does it mean parallel? So how do you well, you see, the definition of parallel is usually using some other lines. So you see, this is the shortest distance between 2 points. That is a line. So you have 2 lines, and you just draw 2 other lines. You draw 2 other lines that make the same angle with your straight line. So then you know that they are parallel to each other. That's the definition of parallel. So these parallel lines, they both go to the pole. Do you agree? Well, I mean, let's forget about the light for the time being. I'm just drawing, as your friend had said, first of all, I define what a line is. In the case of the sphere, it is just big circles. Circles on the surface of the sphere, and their center is the center of the sphere. These are our straight lines on the sphere. Now, what do they tell us? Well, you see here, this is a line as straight as it gets, this is one of the equators. Then you just take 2 points, and from those 2 points, you just draw 2 other lines parallel to each other. Parallel meaning that they both make the same angle with this straight line. In this case, 90 degrees. But if you would follow them, both of those lines, well, this is just like the longitude. Anyway, forget that. So they will both go to the pole. So what happens? The distance gets smaller and smaller. So if these are light beams, if there is a region of space of this shape, you will say that, oh, these two light beams are approaching to a center. You would say that there is a force acting on them, although they are going on straight lines.
So this surface is not plane.
This is a sphere.
Yes, it's sphere.
It's the surface of the sphere. So on the surface of this is an example of a curved space. If you have a curved space, and if you move along straight lines on this particular curved space, if you move along these parallel lines, those lines approach each other, and which we interpret as an attraction between them. So this is basically what Einstein says. So basically he says that there is no force. But what masses do is masses curve space-time. Since space-time is curved, as objects move along straight lines, they are called geodesics, they approach each other, like in this example. And since they approach each other, we interpret it as a force. So what he says is that if you want to calculate the trajectory of objects, let's say, first you have to determine the geometry of space-time. Once you determine the geometry of space-time, then you have to determine the straight lines on that space-time. And those straight lines will give you the trajectories of objects, which will approach each other or get away from each other, etc., which you interpret as being exerting forces on each other. And then he, of course, worked out all the predictions, etc. And another prediction was, one prediction was the bending of light. It was kind of easy to explain. The other one was the motion of planets around the sun. There was this problem of the precession of Mercury. So if this is the sun, what Kepler told us is that all the planets should go around elliptical orbits around the sun. Well, of course, the picture is not so simple in the sense that if you look at the motion of Earth, the dominant influencer on the trajectory of Earth is the sun, but there are all the other planets. They are also exerting additional forces. So there will be some deviation from this due to the other planets. And the orbit turns out to be not perfectly elliptical. But what actually happens is you come here, the ellipse does not perfectly close on its own. Its axis rotates. Well, this is a bad figure. You see, initially the principal axis was along this line, so with time it precessed, it rotated. And you can calculate the effects of all the other planets, etc., and to determine how much it should precess. There were some failures. One of them was, I think it was the Jupiter. The calculations for Jupiter didn't match the observations. So people said that, okay, so there should be some other gravitational influence which we do not know. And then they said that, okay, in order to explain this precession, there should be another planet. And now we discovered that. And then there was another problem with the orbit of Mercury. We calculated all the influences of the planets, and we had discovered that it's not enough to explain. So what you do, you already have one recipe which was successful in even discovering a new planet. Well, you apply the same recipe. So people said that, okay, there should be another planet in order to explain this precession of Mercury. And they tried to calculate where it should be, and they named it Vulcan. If you are a Star Trek fan, Mr. Spock is from the planet Vulcan. That's where the name comes from. And if you remember in the Star Trek movies, the planet Vulcan is a very hot planet. There's nothing green, etc. Because the planet Vulcan, which was speculated to explain the precession of Mercury, it had to be inside the sun. So it had to be very hot. So that was the hypothetical planet. But then when Einstein wrote down his theory of general relativity, using this curvature of space-time, etc., he could calculate that the precession of Mercury without the need of the planet Vulcan. So that was another success of general theory of relativity of Einstein. And if you would like to learn more details, I'm not the correct address for that. You should either go and talk with Bayram Hoca or take the course 482, Special Theory of Relativity 2. That is where you can learn more detailed general theory of relativity. Okay, let's give a 10-minute break and then we will continue with the other topic.